Okay, in this video, we're going to look at the kinematics equations and see which ones are appropriate to use in certain instances. That's really kind of the hardest part about this, is you have a whole bunch of equations, but you need to figure out which one to use. So sometimes that can be a little tricky. So our first equation, okay, you know you had it right in 6th grade. Remember, distance equals rate times time? Okay? That works. That works. You can use this when you have no acceleration, or if you know the average velocity. Okay? This rate here is your average velocity. So sometimes we will use distance equals rate times time, and sometimes it will be that easy. Okay? But this is when there's no acceleration, or if you do have an acceleration, you do know the average velocity. So sometimes this is the easy way to solve things. But the other three that we're going to use are the position, remember, x is position, 1/2, ooh, this one's ugly, at squared plus v initial t plus your initial position. Okay, so most of the time, you guys, most of the time this initial position is going to be 0. So most of the time you're going to start at 0. So most of the time you're not going to use that. Every once in a while you will. So I leave it in there as part of the equation. Every once in a while it'll be there, but most of the time it is not. So that's one equation. The other is your final velocity is equal to the acceleration times time plus your initial velocity. Now, do you notice that I'm making my t's with hooks on them? Okay, I'm making my t's like this. Why do you think I might be doing that? Okay, look at a t and look at a plus sign. If you look at a plus sign and look really closely and you've got a t here next to a plus sign, a lot of times you're going to get those mixed up. So I really encourage you to make your t's with hooks on them so that you can tell, hey, that's a t, not a plus sign. And the last one, which is actually very handy. This one, if you don't know the time and you don't want to find it because you would use it in the first instance, and if you look at the first instance, ooh, yuck, that's a quadratic equation. Yes, this is a quadratic equation too, but it's usually easier to solve. V final squared equals V initial squared plus 2ax. Okay, so our final velocity squared is equal to our initial velocity squared plus 2 times the acceleration times, now this x is your displacement. Alright, so pause the video, write these guys down because you're going to be using these a lot. Okay, this is a partial list of implied information for your kinematics equations. In the problems, they're word problems. Okay, I'm sorry, they're word problems. So you have to be able to pull the information out of the word problems. So some information that's kind of implied. If something starts from rest, that means it was resting in place. And so its initial velocity is 0. Okay? If it comes to a stop, hey, how fast are you going when you stopped? Hey, you're going 0 again. So your final velocity is 0. Now, if you're going at constant speed means that your speed isn't changing. So if your speed isn't changing, your change in velocity is 0. So if your change in velocity is 0, then your acceleration is 0. So constant speed, that's when you can use that distance equals rate times time equation. That's often handy. And then if something's dropped, when it first leaves your hand and you drop it, its initial velocity is 0. Now, there's another piece of information. Its acceleration, gravity is going to pull it down and it's going to speed up every time it falls. We're going to talk more about free fall and throwing things up and down in a later video. but just to get you started, the acceleration due to gravity is 9.8 meters per second squared. So whenever gravity makes anything go down, because gravity only works down, so gravity is always in the down direction, the acceleration due to gravity is 9.8 meters per second squared. So if something's dropped, then gravity's pulling on it. You know, I drop my ball and hey, my ball falls. Why does it fall? Oh, because gravity's pulling on it. So the Earth's gravity is going to cause it to accelerate at 9.8 meters per second squared. So that's just to get you started there. Okay, so here's a few problems from your pretest that have different situations so that we know how to solve these and how to figure out which of those 4 equations we have. Because remember, we have the distance equals rate times time and then the other 3 that have acceleration in them. So here we have Anne driving down a street at 60 kilometers per hour. Suddenly, a child runs into the street. Oh no! It takes Anne 0.78 seconds to react and apply the brakes. How far will she have moved before she begins to slow down? So, we know Anne is still going at 60 kilometers per hour. She's still going at 60 kilometers per hour, so she's going at constant speed. So constant speed, or she's not speeding up, she's not slowing down, that's a big hint that we can use distance equals rate times time, which is going to make our life really, really, really easy. Okay, now we have an issue here. Do you see our speed? Pay attention to these things. See your speeds in kilometers per hour? You need to convert that to meters per second, referring to your previous video. Remember, you did derived units. So see if you can pause the video and see if you can change your 60 kilometers per hour to meters per second. Okay, you paused the video, right? Did you come up with 16.67 meters per second? If you didn't, this is how I got it. So follow this process. Change my kilometers to meters. And then I know 1 hour is 60 minutes and 1 minute is 60 seconds. Or I could have just said that 1 hour is 3,600 seconds. Because remember, that was something we wrote down also. Okay, so distance equals rate times time. Our distance is equal to our rate. And we're going to use the 16.67 meters per second times our time, 0.78 seconds. Okay, and see how the seconds cancel out? And so when we multiply that, we get 13 meters. Okay, 13 meters. So think of 13 meter sticks end to end. That's longer than the classroom. That's even before she can start to apply her brakes and stop. So you can see how difficult it might be to stop when you're going 60 kilometers per hour, which is really only about 45 miles per hour. Okay, here we go again. A particle moves according to the equation x equals 10 meters per second squared times 10 times squared, where x is in meters and t is in seconds. This again is number 22 and 23 from your pretest. Find the average velocity for the time interval from 2 to 3.16 seconds. So we have that average velocity in there. So that tells us again that we can use distance equals rate times time. Okay? Distance equals rate times time. That rate is either your average velocity or your constant speed. So what we need to do is figure out how far do they travel from this 2.02 seconds to the 3.16 seconds. That's what we need to do. So the equation tells us distance and time. So really all we have to do is plug those times in there to find out what kind of distances we're talking about. So for the first time we have x equals 10 times 2.02 squared. Okay? Because all I did was put the 2.02 in for time. And that'll come out to 40.8 meters. Okay? Now let's try you go ahead and try the 3.16 and we'll compare answers. So pause the video, you try the 3.16. Did you get 99.9 meters? Okay, so how far did he go during that time interval? He went from 40.8 meters to 99.9 meters. So if we take the difference between those two, we find out that he traveled. So the distance he traveled, that's going to go in for distance, is 59 meters. It's pretty much 59, 59.056, close enough. And that's going to equal our rate, which is what we're solving for. Now, how long did it take him to do that? What are we going to do? Find the difference between our two times. And that comes out to 1.14 seconds. So it's our total distance, remember we did this before, divided by our total time. And so we're going to get that our rate is, divided by 1.14, 51.8 meters per second. He is flying. Okay? 51.8 meters per second. All right. Part 2 of 2, same thing. So you try to do that, and I'll put the answer up from the pretest. I hope you paused the video and tried to work it out yourself, but you should have gotten 41 meters per second. In 2.12 seconds, he's gone 44.9 meters. That makes our total distance traveled 4.1 meters in that 0.1 seconds. So you get 41 meters per second. Okay, so those two are constant speed. The next one has acceleration. All right, this is skipping way down in the pretest. Now, here's how you solve these problems. When you have acceleration, we basically have 5 variables. We have x, let's write them down. We have x, we have v initial, we have v final, we have our acceleration, and we have our time. Okay, remember x is our distance, our initial velocity, our final velocity, our acceleration, and our time. So if you list these 5 variables down, okay, and we want to know what acceleration, so that's what we're looking for. It says it has to have a liftoff speed of approximately 125 kilometers per hour. So that means when the plane takes off at the end of the runway, it needs to be going 125 kilometers per hour. Now, what do we have to do to that? Do you remember? Pay attention. Kilometers per hour. So what do we have to do that? Correct. Change it to meters per second. So pause the video. Pause the video. So you should have gotten 31.4 meters per second. Now let's think about what a plane does when it takes off. Let's see. Does it have an initial speed? Usually when planes take off, they start at rest, don't they? Right? So its initial speed is going to be 0 meters per second. And then we know that the runway is 251 meters. So we're going to go ahead and put that in for x. Okay, so now we've got everything out of our problem, and that's going to make our life easier to do. So go back to the page where you have your equations. Here's what you want to do. You want to see how nobody said anything about time. We don't have a time given at all. We know our displacement, we know our initial, we know our final velocity, and we're looking for acceleration, but nobody said anything about time. So the easiest way to do this for me, you may find it different, I used to say, go find an equation that has those 4 variables in it. And yeah, you can do it that way. I used to say that. But now here's what I say. Find an equation that doesn't have time in it. Because there's only one equation that doesn't have time in it. And the only equation that doesn't have time in it, go look. Pause the video, go look. The only equation that doesn't have time in it is v final squared equals v initial squared plus 2ax. So we know our final velocity is 31.4, and don't forget to square that. That's going to equal 0 squared, because remember we started out at 0, plus 2 times a, that's what we're solving for, times 251. That's a 251. Okay, so solving for a, no, I am not doing the algebra for you. So let's solve for a. Pause the video. Go ahead and do the algebra. Solve for a. You should have gotten an acceleration of 1.96 meters per second squared. Okay? So far so good? Okay, if you have questions, write them down so that you can ask them when we come to class. Okay, there's two other parts to this problem. So let's make some room for it. What is the corresponding takeoff time? So now we are solving for time. So let's write our variables down just one more time a little bit more neatly. We have that our displacement is 251 meters, because that's how far it's going to go during takeoff. We have our initial velocity as 0 meters per second. We have our final velocity as 31.4 meters per second. We have our acceleration as 1.96 meters per second squared, and we're solving for time. So at this point, we kind of have two equations we could use. Okay, you could use x equals 1/2 at squared plus vit, or you could use v final equals v initial plus at. Okay, either one works. I suggest you use the second. You can use the first. The first one, if we had an initial velocity, so if our initial velocity was something besides 0, this would become a quadratic equation. And you would want to use the quadratic formula to solve it. I'm going to give you the program to program your calculator with the quadratic formula, because we're not spending our tedious time solving for x in a quadratic. So I'll just give you the quadratic formula that you can put into your calculator, and you just tell it what a is, what b is, what c is, and it tells you what the time would be. So sometimes if you use this equation, now sometimes you don't, because if we take out this term, see, for this time, this term drops off because our initial velocity is 0. So we're going to put 0 in there. And so we just have x equals 1/2 at squared. So it's not so bad. But if given the choice, I think I would choose the second of the two. So we know our final velocity is 31.4 meters per second. And that's going to equal 0 plus 1.96 t. So solving for t, we get 15 seconds. And when you're in that plane waiting for it to take off, that seems like a huge amount of time. Alright, so this is part 3 of that same problem. So if the aircraft continues to accelerate at this rate, so the acceleration is still going to be the 1.96 meters per second squared. What speed will it reach? So what final speed will it get to be after it begins to roll? So begins to roll. So before it rolled, it had a speed of 0 meters per second, and then our time is 10.7 seconds. So now we look at our equations, and we want the equation that has these 4 variables and does not have, we want one that does not have x in it. And there's only one that does not have x in it, and that would be the easy one that I told you to use earlier, v final equals v initial plus at. And we're looking for v final, so this is very convenient. We don't have to do any algebra here. 0 plus 1.96, our acceleration times our time, 10.7 seconds. So this is even easier to solve. And we get that our speed ends up being it comes out to 20.97, so we'll just call that 21 meters per second. All right? So hopefully you have a little bit better idea of what to do. List your variables, though. This list of variables will make it a lot easier to figure out what it is you're doing and which equation to choose. Choose the one that doesn't have the variable that they don't give you. And then when you're given, when you could use any of the three, use the one that's the easiest. All right? So we'll have more opportunities to practice in class. I bet you're so excited. I'll see you tomorrow. Bye.